All right, alpha halogenation of enols and enolates, and essentially, you know what we're doing, right? We're gonna get an alpha halogen. Okay, so first thing we're gonna do to understand alpha halogenation of enols and enolates is we're gonna go back and remember what that means. Acid catalyzed keto-enol tautomerism. Take a minute, pause the video now with a blank sheet of paper, and review that mechanism. Okay, suppose that you did. Now come back and looking at this. The enol tautomer can attack a halogen molecule. You've seen this before. This was the halogenation. This looks just like the halogenation of alkenes, right? Exactly the same mechanism. This is very good news. Star. You got good at this in Organic 1, and now it's paying you back. Bam. Bam. Right? And when you, that's going to leave a plus in its wake, so of course this is the new part. Right? These electrons come down and share that, share the orbital with that carbon. All right? Now that we've got that, you've got your protonated carbonyl oxygen, and we deprotonate that exactly as you would expect, and boom, there we go, magic. Now this is essentially an irreversible reaction. To convince yourself of that, draw the backwards of it, and you'll see that the backwards is really nonsense. Draw the reverse reaction, okay? Now this is not irreversible. That's an equilibrium because it's just proton transfer. We see that over and over and over again, back and forth, okay? Now this process is autocatalytic. That is, you're going to get your acid back in the end, and when you get it back in the end, it's likely you still have some Br2, some molecular bromine still in solution, and so you might get a second step of that. Let that sink in. Might happen again. Okay, now when unsymmetrical ketones, pardon the background noise, when unsymmetrical ketones, an unsymmetrical ketone is used, bromination occurs primarily at the more substituted, right? So right here I've got a tertiary, and here this alpha is a secondary, right? And so this is the one that's more likely to happen. All right, the major product results from the more stable or more substituted enol, and a mixture of products is generally unavoidable. So what does this mean? Synthetically of low value. Okay. Now, now that we understand brominating here, we now have a two-step synthesis for an alpha beta unsaturated ketone. All right, we're going to see more of this later in this chapter. Give a mechanism that shows the pyrrole of pyridine. Consider pausing the video here and drawing out this whole mechanism. You have all of it. All right, so draw the whole thing out. Look up pyridine, look up the structure of pyridine, and draw it out also, and that will be excellent practice for you. Okay, other bases such as potassium tert-butoxide can also be used in the second step. It's not going to be a waste of your time to redraw this whole mechanism out again with tert-butoxide. Okay, now go practice with conceptual checkpoints 22.9 and 10, and then when you come back, we'll look at the next slide. Okay, now the HVZ, Hell-Volhard-Zelinsky reaction brominates the alpha carbon of a carboxylic acid. So this is different, right? You see, here's my carbonyl, but this is not an aldehyde or ketone, right? You can't separate that guy out, that hydroxyl. This is a carboxylic acid, and we use the HVZ, Hell-Volhard-Zelinsky reaction to brominate the alpha carbon here. All right, so first of all, the phosphorus tribromide forms the acyl bromide. What is that? Please pause the video and draw the structure of that, the acyl bromide. If you don't know, please consider Googling it. It's going to help you. Search for that. What is an acyl bromide? So, phosphorus tribromide forms the acyl bromide, which more readily forms the enol, and attacks the bromine. That's great. Finally, we hydrolyze the acyl bromide. Okay? And then I'm asking you here now to draw the complete mechanism. All right, go practice with checkpoints 22.11 and 12. And come back and we'll talk more about this. Okay, now alpha halogenation can also be achieved under basic conditions. All right, so in this case, there is no alpha hydrogen here. Here's an alpha and here's an alpha, but there's no hydrogen on this guy, right? So if we take a base and we deprotonate that, what's the pKa of this guy? It's about 19. Okay, so water can take some of that, maybe 18. Okay, so hydroxide, can take some of those protons and make water. All right, and that's an equilibrium process, but when that happens, then you make a nucleophile which attacks this bromine, and that goes off. Okay, now the formation of the enolate is not favored because of the pKa game that we played, right? It's not favored, but the equilibrium process is pushed forward by the second step. So this is irreversible. That means even if it's like that and like this, we're still going to bleed things off in that direction because that second step is irreversible. Now, will the presence of the alpha bromine make the remaining alpha proton more or less acidic? That's a good question. I think I addressed this on the next slide here, but will the presence of the alpha bromine make the remaining alpha proton? Where's the remaining alpha proton? What am I talking about here? It's here, right? That's the second one. So the question is that going to be more or less acidic? Is this going to be faster or slower? All right, so it's faster, actually. So monosubstitution is not possible. Well, that's why. I sort of just cut my question short here. Monosubstitution is not possible. If this doesn't make sense yet, go back and look at that previous slide. Now, methyl ketones can be converted to carboxylic acids using halogen and hydroxide because monosubstitution is not possible. All right, so sodium hydroxide deprotonates this guy. Sodium hydroxide deprotonates that hydrogen right there, right? We put a bromine on there, but it can't stop, so it's going to actually deprotonate all three, right? And when we deprotonate all three, not all at once, right? One at a time, and replace it with a bromine, then the next hydrogen comes off faster, then the next hydrogen comes off faster yet. Once all three alpha protons are substituted, the CBr3 group becomes a decent leaving group. All right? It becomes a decent leaving group. Actually, that's not a plus. Right? Okay. So let's look at that more specifically. Once we have the CBr3 group on there, because we've substituted all three of them, the hydroxide comes in. You've seen this. This is acyl. Addition. Elimination. We got that a lot in the past couple chapters, right? So you've seen this before. We make a decent leaving group. Hydroxide comes in, kicks the electrons up. These electrons come back down. Bam, leaving. And wham, look at that. we now have replaced what was a methyl group in the beginning with a hydroxyl. So we've taken a methyl ketone and we've made it a carboxylic acid. Okay? Now, this haloform is going to deprotonate that, of course, right? And we'll be left with boom. Right? Carboxylate. All right? So we chase that with acid. And we're done. Now, the reaction works well with chlorine, bromine, and iodine. It is known as the haloform reaction. I'm not so familiar with this reaction that I call it like that all the time. I'm not sure what I'm going to call it in class. Sorry, pardon me for the background noise. I'm working here in my dining room, so as always. All right. So the iodoform reaction may be used to test for methyl ketones because iodoform, where am I here? Iodoform can be observed as a yellow solid. It's a precipitate. So CHI3 precipitates. Okay, now go practice with conceptual checkpoints 22.13 and 14 and then come back. I think we've got one more slide in this presentation. Okay, yeah, we do. So now give the major product for the reaction below. Oh, it's chlorine. Sorry, I thought that was iodine. I was thinking that was iodine with a typographical. It's chlorine. Okay, excess chlorine in sodium hydroxide, and tell what happens. All right, I'm not going to give you the answer. I'll give you the answer in class if you like. Bring it to class with you. I'd like to see your notes on it, and I'll see you in section 3. Good luck.